Math 111. Today we're going to finish section 7.1 in a part 2. Be sure to denote that we talked about 7.1 part 1 in an earlier video lecture. Going to finish that today. 7.1 part 2 and 7.3 we're going to talk about simplifying radical expressions. So let's finish section 7.1, radical expressions. Alright, we talked about all kinds of radical type expressions in 7.1, but we were restricted to square roots or second roots and cube roots or third roots. Now, not all roots, of course, fall into those categories. There's fourth roots, fifth roots, 20th roots, 100th roots, and ad infinitum. Well, we're going to talk about here finding nth roots, where n can be really any index, not restricting ourselves to 2 or 3. Well, let's see. Let's jump right in. And the underlying idea is kind of the same. The problems get quite a bit more complicated in this situation. Well, let's start out with an easy one, the fourth root of 16. Well, as you know from the part 1, this is the number I raise to the fourth power to get 16, just like with square roots and cube roots. In other words, I'm asking what quantity will I raise to the fourth power to get positive 16? And of course you'll say that number is 2. The fourth root of 16 is 2. Let me erase the question mark and fill this in. Oops. Slipped. The fourth root of 16 is 2, and I say because when I raise 2 to the fourth power, I do indeed get 16. So again, you're reversing or inverting the fourth power operation. Just like 2 to the fourth is 16, the fourth root of 16 is 2. Let me put that down. If 2 to the fourth power is 16, if I plug that in, let me write it like this. If I plug 2 in to the x to the fourth machine, 16 comes out, and if I plug 16 into the fourth root machine, then 2 comes out. So you can see these two different machines, or functions if you will, reverse or invert each other. Okay? Let's talk about other higher order roots. By that I mean higher than 2 or even 3. How about the fifth root of 243? By definition, this is the number I raise to the fifth power to get 243. I'm asking, what number do I raise to the fifth power to get 243? And of course, that's 3. Now, hopefully, I think the idea is you get more familiar with practice at certain powers of certain bases as you go up the line here. 3 to the fifth power is indeed 243. So I claim the fifth root of 243 is 3 because 3 to the fifth power is 243. In other words, 3 is the number I raise to the fifth power to get 243. Now let's talk about some nastier ones here. Remember we said in part 1 it's okay to have a negative radicand if your index is odd. Right? The seventh root of minus 128. Well, I notice, let's see, minus 128, does that sound familiar to us? Certainly it is a real number. It's okay to have a negative radicand when your index is odd. What I'm asking here is, what number do I raise to the seventh power to get a negative 128. Alright, well, maybe you don't see it right away. If I note that 2 to the 7th power, that's 2 times 2 times 2 times 2 times 2 times 2 times 2, that's 7 factors of 2. 1, 2, 3, 4, 5, 6, 7. That's 128. Right? Well, if I realize that, then if I put a negative 2 in this base, then negative 2 to the 7th power is going to be negative 128. An odd number of negative factors will give you a negative return. So, the long and short of it is, the 7th root of minus 128 is negative 2. Let me put that again. It's okay to have a negative radicand if the index is odd. Okay, we saw a touch of that last time in part 1. Let's try something that looks like this. How about if I ask you the 4th root of 81? Well, of course, at this point you're going to return to me the 4th root of 81 is 3, because 3 to the 4th power is 81. How about if I ask you the 4th root of negative 81? Well, let me put a question mark there for a minute. You're asking here, what number do I raise to the 4th power to get negative 81? And of course we can see, because this exponent is even, no matter what number I plug into this base, I will never get a negative number. If I've got an even string of negative factors, the return will always be positive. So I claim in this situation it's not a real number. So in other words, you can't take an even index root of a negative quantity. So let me kind of informally write this. You can't have a even index root of a negative radicand. Again, that's in somewhat informal language, okay? Alright. I'm going to maybe a little more formally talk about the nth root of A. Let me try to define it. That's a symbol for definition. This is the number or quantity, because we could have variables. We're not always going to be working with numbers here. So I'm going to say it's the quantity you raise to the nth power to get A. Okay? Alright, so this is a somewhat more formal definition of what it means to take the nth root of a number. Let's try some more higher order roots, higher index roots. If I've got here the 4th root of 625, what is the 4th root of 625? It's 5. And if I ask you why, you'll of course say, because 5 is the number I raised to the 4th power to get 625. 5 times 5 times 5 times 5 is 625. If I ask, what's the 4th root of minus 1? You'll tell me this is not real, for reasons we've just talked about. You cannot take an even index root of a negative quantity. How about the 7th root of 10 to the 7th power? Now, I don't need to multiply 10 times itself 7 times to see that the answer is 10, right? Because this power operation and this root operation are inverse operations. They basically undo each other, and I get back what I started with here, namely number 10. All right? Perhaps more informally, I can say the 7th root of 10 to the 7th power is 10 because 10 is the number I raise to the 7th power to get 10 to the 7th power. Similarly, the 6th root of 64. Well, hopefully we're getting more and more familiar with powers of 2, powers of 3, powers of 4, etc. as we march through Chapter 7. The 6th root of 64 is 2. Why? Because 2 is the number I raise to the 6th power to get 64. Please convince yourself that 2 times 2 times 2 times 2 times 2 times 2 is indeed 64. Alright, how about variables? Higher order roots when variable expressions are involved. Right? The 5th root of x to the 5th power is, of course, x. X is the quantity I raise to the 5th power to get x to the 5th power. Alright, no sweat there. How about the 4th root of 16, x to the 4th power? Well, the 4th root of 16 is, of course, 2. The 4th root of x to the 4th power is x. And again, we'll agree, and again, this is by definition, that even index roots must be positive. So if we don't make some sort of claim that variables represent positive quantities, you'll have to wrap that answer in parentheses, an absolute value symbol. Right? If we make this claim, if we assume x is greater than 0, in other words, if we assume that all variables represent positive quantities, I can just write my answer as 2x. So I just want to be sure that you realize where these absolute value symbols are coming from in our answer guide, homework solution type guide, those PDF files. Let's see, the 4th root of 81, x to the 8th power. Well, as you might realize, we can take the number first. The 4th root of 81 is, of course, 3, because 3 to the 4th power is 81. The 4th root of x to the 8th power, that's x squared, because x squared to the 4th power is indeed x to the 8th. So be sure to convince yourself that the 4th root of x to the 8th is x squared. 3x squared is the return there. I'll do a couple more here. I'll say the square root, let's call this 6th root of k to the 12th power. And notice I always try to terminate my square root symbols, or my root symbols, kind of definitively, so I know what's in under the root sign and what's not. Probably a good habit to get into. The 6th root of x to the 12th. The 6th root of k to the 12th power is what? Well, whatever it is, when I raise it to the 6th power, I need k to the 12th. Right? So clearly, I can see that k squared goes on in that parentheses, right? So k squared is the 6th root of k to the 12th because k squared raised to the 6th power is indeed k to the 12th. Let me get a fresh screen here. How about if I ask you to simplify the following radical expression? Minus 144 t squared. Now remember, when no index is specified, we assume a second root or a square root, right? So I want really the square root, or negative the square root of 144t squared. Now, notice this negative sign is outside this square root operation. So it's just like having a multiplier of -1 hanging out outside that root sign. So maybe write that a little more clearly. So there's no negative sign inside this even index root, so I can go ahead and perform the operation. I'll get -1 times, well, the square root of 144 is 12, and the square root of t squared is, well, again, formally it's the absolute value of t, and if we assume that variables are representing positive quantities, I could rewrite this as -12t. Again, with that assumption. Let's try another one here. The fifth root of -243. Now remember, it's okay to have a negative radicand when your index is odd. Alright, I need to ask myself, what number can I raise to the fifth power to get -243? Alright, well, I think we can try 3. Well, what's 3 to the fifth power? 3 times 3 times 3 times 3 times 3. Well, 3 times 3 is 9. 9 times 3 is 27. And 27 times 3 is 81. And 81 times 3 is indeed 243. Alright, so clearly now this is going to be -3. The fifth root of -243 is -3. I'll call that my final answer, and I say that's true because -3 to the fifth power is -243. If you need to convince yourself a little more fully, I can write out a string of 5 factors of -3, and anytime you've got an odd string of negative factors, you're going to end up with a negative return. And I know that 3 times 3 times 3 times 3 times 3 is indeed 243. So that's my final answer. One more before we go on to the next section. If I'm asked, I believe this is in your homework list, the cube root of -216 z to the 9th power. Alright, now again I like to consider the coefficients first. The cube root of -216 is -6. Check it out, -6 times -6 times -6 is -216. And the cube root of z to the 9th power, well, that's going to be z cubed, because z cubed to the 3rd power is z to the 9th. Alright, so my final answer for this problem would be -6z cubed. Alright, so in part 1 we talked about square roots and third roots or cube roots, and in this part 2 we talked about higher order roots, 4th, 5th, 6th, and even higher index roots. I want to now go on to section 7.3. And section 7.3 is entitled Simplifying Radical Expressions. And it is a bit of an extension of what we learned in section 7.1. Suppose I ask you to simplify something like this: the square root of 12. Well, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and we're too big. So, well, the idea here is 12 is not what we call a perfect square. Well, what is a perfect square? A perfect square is a square of a whole number or integer. Okay? Right? Well, 12 is not a perfect square, but it contains a factor of 4 that is a perfect square. I think we've all played this game before. I can break up 12 as 4 times 3, and I do that because 4 is a perfect square. As you might have guessed, we can break up a root sign over a product and multiply the results. Right? The root of a product is the product of the individual roots. The square root of 4, of course, is 2. The square root of 3 is just the square root of 3. Can't really simplify that any further. So my final return for this answer would be 2 times the square root of 3, or what some people sometimes say, 2 root 3. Remember, there's an implied multiplication here in this final answer. 2 times the square root of 3. We call this simplified radical form. And you are in simplified radical form, well, in kind of common language, when you've taken out everything that you can from under the root sign. Alright, let's do some harder ones here. Simplify. The square root of 98. Well, 10 squared is 100, so it's going to be something less than 10. But 98 clearly is not a perfect square. But of course it contains a factor of 49. And 49 is a perfect square. And again, I can break up a root sign over a product. So equivalently, this is 7 times the square root of 2, or what most students might call 7 root 2. 7 square roots of 2. Again, this is simplified radical form. Try another one. Alright, this game doesn't just happen with square roots, as you might imagine, with third roots, fourth roots, etc. What's the third root of 54? Well, let's take a look. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 81, and we're already too big. So clearly 54 is not going to be on this perfect cube list. This is a beginning list of all my perfect third powers, and you go on forever. Well, the idea here is 54 does not appear on this list, but 27 does, and 27 is a factor of 54, is it not? I can rewrite 54 as 27 times 2, and my motivation for that, essentially I can take out the factor of 27 from under that root sign. The cube root of 27 is of course 3, and the third root of 2 can't be reduced any further. Right? So again, you're in simplified root form when you've taken out everything you can from under the root sign. Be careful to denote your index and your final answer. Not every root is a square root, and when you're not a square root, you've got to specify your index. Okay? Let's try a fourth root in this same idea. I'll say, well, how about if I ask you something like this? Simplify minus the fourth root of 48. Now again, when that negative sign is outside of the root symbol, I can just treat it as a factor of minus 1 after I complete the root process, okay? So don't be thrown by that negative sign outside the root. Alright, so I'll say this is minus 1 times, well, 48 is not a perfect fourth power. 1 to the fourth is 1. 2 to the fourth is 16. 3 to the fourth power is 81, and we're too big, bigger than 48. So, again, these are my perfect fourth powers, and 48 is not on this list, but it contains a factor of 16 that is on this list. So, what I can do and say, well, 48 is not a fourth power, but 16. 48 is 16 times 3, is it not? And 16 is a perfect fourth power. Alright, so I claim this is now minus 1 times the fourth root of 16 times the fourth root of 3 minus 1 times, then the fourth root of 16 is 2. The fourth root of 3 can't be reduced any further. 3 is what I call a residue factor that has to stay inside the root symbol. Well, outside minus 1 times 2 is, of course, negative 2. So I'll call my final answer here minus 2 times the fourth root of 3 in simplified radical form. Get a fresh screen. Alright. How about simplifying the fifth root of 128? Now we start getting a little larger in magnitude, of course, with the values when we start talking about fifth powers, sixth powers, eighth powers. We get very big very quickly. Let me make a list of perfect fifth powers. 1 to the fifth, oops, common mistake there. 1 to the fifth is not 1, or not 5, I mean. 1 to any power is 1. So 1 to the fifth power is 1. 2 to the fifth. 2 times 2 times 2 times 2 times 2. That's 32. 3 to the fifth power. I think that's 243, isn't it? We're way too big already. So, and if I'm looking for the fifth root of 128, I can see 128 does not appear on this list. But I think we can see that 32 is buried in here as a factor of 128, is it not? And 32 can come out from under the root sign. So I'll say that the fifth root of 128 is equal to the fifth root of 32 times 4, is it not? 4 times 32 is 128. And after a while you start skipping steps on these. I suppose you don't have to write down each and every step, and some of these problems will be here all day. So the fifth root of 32, well, I know what that is. That's 2 times the fifth root of 4 can't be reduced. We've taken everything out that we can. So my final answer would be 2 times the fifth root of 4 for this exercise. Alright, simplifying radical expressions. Alright, we've done a bunch of these with numbers. How about with variable expressions? Well, variables can get reduced or simplified in this way also. Simplifying the square root of m to the 9th power. Now again, when you have no index specified, we're assuming an index of 2, or square root, right? Alright, now the idea here is you can, let me leave the index there, let me put it back. You can take out from under the root symbol as many powers of your variable that are multiples of your index. Well, the highest multiple of 9, the highest multiple of 2 that's less than 9 is 8. Well, let me write it out this way. I claim I can rewrite m to the 9th as m to the 8th times m to the first power. Because 8 is a multiple of 2, I can take all these factors of m to the 8th out from under the root sign, and one factor of m is going to be left inside as what I call a residue factor. Okay? Let me write this out again. So the square root of m to the 9th is equivalent to the square root of m to the 8th times m. And I can break up any root sign over a product. The square root of m to the 8th is m to the 4th power, is it not? Why? Because m to the fourth squared is m to the eighth times the square root of m. Will have to be a residue factor of m that has to stay inside the root symbol. Alright, a little more informally, I'd write my answer like this. This would be m to the fourth times the square root of m. This would be my completely most simplified answer to the stated question, the square root of m to the ninth. I'm going to write the original problem down here. It's lost upstream. So if I'm asked to simplify the square root of m to the ninth, this would be your final return. Let's play this game with some more variable type expressions. How about the square root of 128 a to the fifth power? Alright, again, when no index is specified, we're talking about a square root. Alright, let me skip some steps here. 128 is not a perfect square, but it contains a factor of 64 that is. So what I like to do in this type of problem is pile up the factors that are coming out on the left-hand side. I can do that because multiplication is commutative. Alright, so 128 is 64 times 2. And a to the fifth power, well, I claim 4 factors of a can come out. That means one factor of a has to stay inside. The square root of 64 is 8. The square root of a to the fourth is, of course, a squared. And 2a, the factors 2 times a, has to stay inside the root symbol. So again, I'm in simplified radical form when I get everything out from under the root sign that I can. Let's try another one, a little nastier one. This one's a cube root. Alright. If I ask us to simplify, give you some more room here. If I ask us to simplify the third root of minus 24x to the fifth. Well, 24 is not a perfect third power. X to the fifth is not a perfect third power. If it was, it would be the exponent would be a multiple of 3. Well, what I can do is take some of this stuff out, and some of the stuff's got to stay inside. Minus 24 is not a perfect third power, but it contains a factor of minus 8, which is, well, minus 24 is negative 8 times 3. Similarly, x to the fifth power is not a perfect third power, but it contains a factor of x cubed, so I can rewrite that variable portion as x cubed times x squared. Alright, so these two factors can come out from under the root sign. The cube root of minus 8 is minus 2. The cube root of x cubed is just x, times the cube root of whatever's left inside, namely the cube root of 3x squared. This would be my completely simplified answer for that question. So you got two more I want to talk about today. And let's ask us to simplify the fifth root of a to the ninth, b to the seventh, times c to the fifth. Alright, the long and short of it is, some of these powers of these variables can come out from under the root sign, and some of them can't. Alright, what I'm going to do is pile up the powers of a, b, and c that will be able to come out. Namely, 5 factors of a can come out, 5 factors of b can come out, and 5 factors of c can come out. Times, well, how many stay inside? Well, I'll have 4 factors of a left, I'll have 2 factors of b left, and I'll have no factors of c left inside because they're all piled up in this slot. Alright, so the fifth root of a to the 5th power is just a, no root sign. The fifth root of b to the 5th power is b, outside the root sign. The fifth root of c to the 5th power is c, times the fifth root, don't forget that index, of a to the 4th times b squared. You'll notice that both these exponents here are less than your index. If you have an exponent left inside that's higher than your index, you're not completely simplified. So let me rewrite this answer. ABC times the fifth root of a to the 4th, b to the 2nd. This would be my completely simplified answer for that one. Okay? One more and we'll call it a day. This is number 102 in the text. The fifth root of 243 times r to the 22nd power. Alright, things are getting a little nastier here. Well, if I'm looking for perfect fifth powers from under this root sign that can come out, well, let me think. 1 to the 5th power is 1. 2 to the 5th power is 32. 3 to the 5th power is 243. Alright, so it looks like, it looks like 243 is going to be able to come out, right? 3 times 3 is 9. 3 times 9 is 27. 3 times 27 is 81. And 3 times 81 is 243. Alright, similarly, r to the 22nd power. Well, some of these powers of r can come out from under the root sign. You can take out as many powers of r that are multiples of your index. Well, the highest multiple of 5 implied in this exponent is 20, is it not? So what I'm going to do, again, I'll pile up the factors that are coming out on the left side of this radicand and just rewrite it as this multiple. Alright, so 243 is coming out because that's a perfect fifth power. R to the 20th is coming out because that's the largest perfect fifth power. That's a factor of r to the 22nd, but the r squared has to stay inside. The fifth root of 243 is 3. We've already established that. The fifth root of r to the 20th power. Can you figure it out? Let me give you a minute. What's the fifth root of r to the 20th power? It's r to the 4th. Why? Because r to the 4th to the 5th power is r to the 20th. Times what's left inside? The fifth root of r squared. Don't forget to specify that index. It's easy to get exponents to mush up with the indexes on these roots, to be sure, so be sure to express your answers clearly. Final answer, 3r to the 4th times the fifth root of r squared. I got everything out from under that root sign that I could, okay? Alright, so we're reaching 39 minutes, so we're going to call it a day. In section 7.1 part 2, section 7.1 part 2, and section 7.3. That's all.